Right now, you are floating inside a cosmic crime scene. Your solar system sits in a bubble carved by exploding stars, surrounded by invisible matter that weighs more than everything you can see. Above us and below us, structures stretch thousands of light years into darkness. A ring of ancient supernovae blasted our neighborhood empty. Dark matter wraps the galaxy in a halo we cannot touch. The Milky Way's gravity shakes frozen comets at the edge of the sun's reach. Picture the Milky Way as a spinning disk of stars, flat, wide, packed with light. Most stars crowd near the middle, hugging that central plane where gravity holds everything tight. You would think our sun lives there too, pressed into that cosmic flatline with all the others. It does not. Our entire solar system floats 55 light-years above the galactic midline, that is 324 trillion miles north of where the galaxy is thickest. Scientists confirmed this measurement using gamma-ray telescopes that peer through dust and gas, marking our exact position in three-dimensional space. We are not where we should be. The galactic plane itself stretches 100,000 light-years across, but only 1,000 light-years thick. Think of a dinner plate. The sun should be somewhere in that plate, but instead it hovers above the porcelain, floating in the emptiness between the table and the dish. When you look up at night toward the northern galactic pole, you are staring into a completely different neighborhood than when you look down toward the south. The structures are different, the densities are different. Even the temperature of invisible gas differs between these two directions. Being above the plane means we experience less radiation from the galactic center. That supermassive black hole, 4 million times heavier than our sun, sits 27,000 light-years away. But it is also below us in that dense stellar disk. Its violence gets filtered through layers of gas and stars before reaching our floating position. Some researchers suggest this elevation protected Earth during its early years, allowing life to develop without being scorched by excessive cosmic rays. But our position is not permanent. The sun does not stay at 55 light-years north forever. It moves, it oscillates. It swings up and down through the galactic plane like a weight on a spring, crossing through that crowded stellar disk again and again. We are currently moving away from the plane, heading farther north at about 4.5 miles per second. The last time we crossed through the galactic plane, 3 million years ago, right when early humans started walking upright. Speed shoots past the center and keeps going to the other side. Then gravity pulls it back. The ball oscillates through the planet over and over like a pendulum swinging through vertical space. Our sun does exactly this through the Milky Way. Every 26 million years, the solar system completes one full bounce up and down through the galactic plane and back again. Scientists confirm this rhythm by tracking stellar positions and calculating gravitational forces throughout the galaxy. We are a cosmic pendulum. The galactic disk contains most of the Milky Way's visible mass. Stars, gas, dust, all packed into that flat structure. When the sun floats above the plane like it does now, all that mass below us creates a gravitational tug downward. Every star, every cloud, every particle pulls us back toward the middle. So we fall slowly at first, then faster. We are currently moving north away from the plane, but that motion is slowing down. Eventually, we will stop rising, hover for a moment, then plunge back toward the galactic center line. When we cross through the plane, we will be moving fast, maybe 6 miles per second or more, enough to shoot past the middle and out the other side. Then the same thing happens in reverse. Once we emerge below the galactic plane, all that mass above us pulls upward. We slow down, stop, reverse course, and fall back through the plane again, heading north. The cycle never ends. It is repeated hundreds of times since the sun formed 4.5 billion years ago. But something makes this motion more complex than a simple pendulum. The galactic disk is not the only thing pulling on us. Dark matter, that invisible substance making up most of the galaxy's mass, wraps the entire Milky Way in a halo, extending far above and below the visible stars. This dark matter contributes about 15% additional pull to our vertical oscillation. Scientists calculated this by measuring how fast we move and working backward to figure out what forces could cause that speed. Some researchers proposed something terrifying in the 1980s. They suggested we encounter denser regions of matter every time we cross the galactic plane, and those dense patches shake the Oort cloud, sending comets flying toward Earth. They called it the extinction theory. Major extinction events on Earth, including the one that killed the dinosaurs, seem to line up with our crossings through the galactic plane every 26 million years. The evidence looked compelling at first. Then better dating of extinction events showed the pattern was not as clean as initially thought. The theory fell apart under scrutiny. But we do cross through different environments. The density of gas, the strength of magnetic fields, the intensity of radiation, All of these change as we bob up and down through galactic space, and those changes definitely affect what happens at the edge of our solar system. The pendulum motion means Earth has experienced different galactic neighborhoods throughout its history. Life evolved while the sun traveled through varying cosmic conditions. Some periods were calm, others violent. What waits for us on the next swing through the plane? Nobody can say for certain, but the physics promises we will find out in about 30 million years, unless something else reaches us first. Something already closing in from the void we float inside. You live inside a bubble 1,000 light-years wide. The walls are made of compressed gas. The interior is nearly empty. One of the most extreme vacuums astronomers have ever detected in space. This is not a natural formation. This is a crime scene. Scientists call it the local bubble. They confirmed its existence using multiple methods, including X-ray telescopes that mapped the hot gas defining its boundaries, and optical surveys that showed where nearby stars cluster. Every star within 500 light-years of Earth sits on the surface of this bubble, not inside it. We float in a cosmic cavity carved by violence. The inside of the bubble contains about 1,000th of an atom per cubic centimeter. That is 10 million times less dense than the air you breathe. For comparison, the best laboratory vacuum humans can create is still 10,000 times denser than a typical interstellar cloud, which itself is thousands of times denser than the local bubble. This void is absurdly empty, but the gas inside is hot, not warm but hot, about 1 million degrees Kelvin. Meanwhile, the local interstellar cloud immediately surrounding our solar system is merely warm at 7,000 degrees, with a density of 0.3 of an atom per cubic centimeter. Two completely different environments pressed against each other. How does gas reach 1 million degrees in the middle of nowhere? Only one thing produces that kind of heat: supernova explosions. Multiple supernovae, massive stars detonating in sequence, each blast feeding energy into the expanding cavity, heating the interior to temperatures that would vaporize anything solid instantly. Astronomers traced the evidence backward. They studied the motion of nearby star clusters and calculated when massive stars in our neighborhood would have exploded. The timeline pointed to 10 to 20 million years ago. Not one supernova, but several, possibly as many as 15 or 20 separate detonations. Each explosion added energy to the bubble, pushing its walls outward, sweeping up gas and dust, creating the void we now inhabit. Think about what that means. Our solar system was already here when those stars exploded. Earth existed, life thrived in the oceans, and somewhere out in our galactic neighborhood, massive stars reached the end of their fuel supplies and detonated one after another in a cosmic chain reaction. Each blast sent shock waves expanding at thousands of miles per second. Each one heated the surrounding gas to millions of degrees. The bubble grew larger with every explosion. We survived it barely. The shock waves weakened as they traveled outward. By the time they reached us, assuming we were near the edge of the forming bubble, the violence had dissipated enough not to destroy Earth's atmosphere. But the evidence suggests something more terrifying. We might have been inside the bubble as it formed, caught in the expanding cavity, bombarded by radiation and high-energy particles for millions of years. Scientists recently discovered we are in the process of emerging from the local bubble. Our trajectory will take us out of this void in several million years, assuming we do not encounter another dense cloud first. But the bubble itself is not finished. It continues expanding even now, though more slowly than during the initial blasts. The walls push outward into surrounding space, compressing gas at the edges, potentially triggering new star formation. And every star has a lifespan. Every massive star eventually explodes. The local bubble is surrounded by young bright stars in a structure called Good's Belt. Some of those stars will go supernova in the future. The crime scene is not cold yet. The killers might strike again. 15 massive stars died to create the space you call home. Each one burned brighter than our sun ever could, lived fast, exhausted its fuel in just a few million years, then exploded with more energy than our sun will produce in its entire 10 billion year lifetime. These were not distant events. These happened in our neighborhood. The best candidate for triggering the local bubble is a group of stars astronomers called the Scorpio-Centaurus Association. This collection of massive hot stars sits about 400 light-years away, right on the edge of our bubble. Here is how a supernova creates a bubble. A massive star, maybe 20 or 30 times heavier than our sun, fuses hydrogen into helium in its core, then helium into carbon, carbon into oxygen. The fusion continues up the periodic table, creating heavier and heavier elements. But when the core starts fusing iron, the process stops producing energy. Instead, it consumes energy. The core collapses in less than a second. Matter falls inward at nearly a quarter of the speed of light. The collapse happens so fast that the outer layers do not have time to react. They hang in space for a moment, suspended, while the core implodes beneath them. then the core bounces. The rebound sends a shock wave exploding outward through the star's outer layers at thousands of miles per second. The star tears itself apart. The explosion releases more energy in a few seconds than 100 billion normal stars produce in the same time. That energy blasts outward in all directions, heating surrounding gas to millions of degrees, accelerating it to supersonic speeds. A supernova remnant expands like a cosmic bomb crater, growing larger every year. Now imagine 15 or 20 of these explosions happening in the same region of space over 10 million years. Each blast adds energy to the expanding cavity. Each one pushes the bubble walls farther outward. The combined effect creates a structure far larger than any single supernova could produce. This is called a superbubble. Scientists found physical evidence these explosions affected Earth. The proof sits in deep ocean sediments. When researchers drilled cores from the ocean floor and analyzed the layers, they discovered elevated concentrations of iron-60, a radioactive isotope that does not form naturally on Earth or in our solar system. The only known source is supernova explosions. The iron-60 peaked twice, once about 1.7 to 3.2 million years ago, and again about 6.5 to 8.7 million years ago. Both peaks correspond perfectly with the time our solar system would have crossed through debris clouds from the supernovae that created the local bubble. The radioactive atoms fell from space, settled in the ocean, and stayed there as evidence. The proof is buried in mud at the bottom of the sea, and we do not know exactly where the solar system was positioned when those explosions happened. We might have been near the edge of the forming bubble, relatively safe, or we could have been much closer to the detonations, exposed to far more radiation than Earth's magnetic field and atmosphere could easily handle. The radiation levels could have influenced mutation rates in life on Earth, possibly accelerating evolution during those periods. We survived. But what changed inside us because of it? Nobody knows yet. Right now, Earth is flying through a cloud, not a weather cloud, but an interstellar cloud made of hydrogen, helium, and trace amounts of heavier elements. This cloud surrounds our entire solar system, wrapping us in a cocoon of warm gas that extends several light years in every direction. Scientists call it the local interstellar cloud, and it is moving. The cloud itself measures about 30 light years across, though its exact boundaries remain fuzzy because gas densities gradually decrease toward the edges rather than stopping abruptly. The temperature sits around 7,000 degrees Kelvin, which sounds hot but qualifies as merely warm by interstellar standards. The density measures 0.3 of an atom per cubic centimeter. For comparison, the air you breathe contains about 30 billion atoms per cubic centimeter. This cloud is almost empty, yet it is still 300 times denser than the local bubble that surrounds it. The cloud is moving relative to the solar system at about 16 miles per second, but the solar system is also moving relative to the galaxy at around 140 miles per second. When you combine these motions, you get something called the local interstellar wind, a flow of gas streaming through our solar system at roughly 16 miles per second from the direction of the constellation Ophiuchus. Scientists confirm the existence of the local interstellar cloud by measuring the absorption of light from distant stars. When starlight passes through gas, certain wavelengths get absorbed depending on what elements are present in the cloud. By analyzing these absorption patterns in the light from multiple stars, astronomers mapped out the cloud's location, temperature, density, and chemical composition. The cloud definitely exists. We definitely live inside it. What makes astronomers slightly nervous is the question of how long we have been inside this cloud. The best estimates suggest we entered the local interstellar cloud sometime between 44,000 and 150,000 years ago, depending on whose calculations you trust. That is extremely recent in cosmic terms. Before that, we occupied a different region of the local bubble with possibly different gas properties, different densities, different temperatures. The cloud is moving through the local bubble, and so are we, but not in the same direction or at the same speed. Eventually, within another 10,000 to 50,000 years, depending on which model you believe, we will exit the local interstellar cloud and enter a different region. Maybe another cloud, maybe empty space within the local bubble. The environment will change. The density of gas around the solar system will shift. The amount of interstellar material flowing into our heliosphere will increase or decrease. Some researchers suggest these changes could affect Earth's climate over very long time scales. More interstellar gas entering the heliosphere might compress the protective bubble slightly, allowing more cosmic rays to reach Earth's atmosphere. Those cosmic rays could ionize atmospheric particles, potentially influencing cloud formation and climate patterns. The effects would be subtle, far too weak to cause an ice age or mass extinction, but possibly strong enough to show up in long-term climate records. Wrapped around our solar system like a tilted crown sits a ring of death. Young, massive stars burn there, stars that will explode within the next few million years. This structure stretches 3,000 light-years across, tilted 20 degrees relative to the galactic plane. Astronomers call it Good's Belt, and it surrounds us completely. The belt was discovered in the 1800s by Benjamin Good, who noticed that the brightest stars in our night sky do not distribute evenly across the celestial sphere. Instead, they cluster along a great circle tilted relative to the Milky Way's main band of light. The belt includes some of the most famous star-forming regions visible from Earth. The Orion Nebula sits within it. So does the Scorpio-Centaurus Association, the same group of stars responsible for the supernovae that created the local bubble. The entire structure is filled with stellar nurseries, places where gas clouds collapse under their own gravity to form new stars. Most star formation in the Milky Way happens in the galactic plane where gas and dust concentrate. But Good's Belt tilts 20 degrees away from that plane, creating a ring structure that rises above and dips below the main stellar disk. The stars in Good's Belt are young by cosmic standards. Most are less than 30 million years old. Some are still forming right now, wrapped in cocoons of dust and gas. These are O-type and B-type stars, the hottest and most massive stars in the galaxy. They burn blue-white, radiating enormous amounts of ultraviolet light. They consume their fuel so quickly that they will exhaust their nuclear cores within just a few million years, then detonate as supernovae. The belt is dangerous, not because it exists, but because it changes. Star formation continues. New massive stars light up inside the ring. Each one is a ticking time bomb with a fuse measured in millions of years. When they explode, they will feed new energy into the surrounding space, possibly expanding the local bubble further, potentially triggering new waves of star formation. Some of these stars have already died. We just have not seen the light from their explosions yet. A star 500 light-years away could have detonated 400 years ago, and the light from that blast is still traveling toward us through space. We would not know until the wavefront arrived. Suddenly, a new point of light would appear in the night sky, bright enough to see during the daytime, lasting for weeks or months before fading. The nearest massive star in Good's Belt currently sits about 400 light-years away. That is close by galactic standards, close enough that a supernova would be visible as a spectacular object in our sky, but far enough that the radiation would not threaten Earth directly. The real danger comes from stars within a few dozen light-years. At that distance, gamma rays and X-rays from the explosion could impact Earth's atmosphere, potentially depleting the ozone layer and increasing surface radiation levels. Your planet exists inside a bubble blown by the sun. This bubble protects you from the galaxy. Without it, interstellar radiation would slam into Earth at full intensity. Cosmic rays would bombard the atmosphere constantly, and life as you know it might never have evolved. This protective shield is called the heliosphere, and it has limits. The sun constantly spews charged particles into space. Protons, electrons, helium nuclei, all accelerated to speeds between 200 and 500 miles per second. This stream of particles is the solar wind, and it flows outward in all directions, filling the space around the sun with a hot magnetized plasma. The solar wind does not stop at the edge of the planetary orbits. It keeps going, expanding outward until something stops it. That something is the interstellar medium. All the gas and dust floating between stars creates pressure pushing inward on our solar system from every direction, where the outward pressure of the solar wind equals the inward pressure of the interstellar medium. A boundary forms. This boundary, called the heliopause, marks the edge of the heliosphere and the beginning of true interstellar space. Then Voyager 1 crossed it. On August 25, 2012, at a distance of 121 astronomical units, Voyager 1 detected a sudden drop in solar wind particles, a sharp increase in galactic cosmic rays, and a change in the direction of the magnetic field. The spacecraft had crossed the heliopause into interstellar space. The measurements confirmed the boundary exists exactly where theory predicted. But the heliosphere is not round. Observations from multiple spacecraft revealed that the heliosphere is asymmetric, possibly teardrop-shaped, or even more irregular. The shape depends on the direction the solar system moves through the interstellar medium, and on local variations in gas density and magnetic field strength. The local interstellar cloud surrounding us pushes on the heliosphere unequally. In the direction we are moving, the heliosphere compresses slightly. In the opposite direction, the heliosphere extends farther outward. Inside the heliosphere, the solar wind shields us from most interstellar particles and galactic cosmic rays. These high-energy particles, accelerated by supernovae and other violent events across the galaxy, constantly bombard our region of space. Most get deflected or slowed by the magnetic fields embedded in the solar wind. Only a fraction penetrate all the way to Earth's orbit. But the shield is not perfect. The sun's activity varies on an 11-year cycle. During solar maximum, when the sun produces more solar wind and stronger magnetic fields, the heliosphere expands slightly and blocks more cosmic rays. During solar minimum, the heliosphere shrinks and weakens, allowing more cosmic rays to penetrate. And the heliosphere changes size depending on what cloud we pass through. When the solar system travels through denser regions of the interstellar medium, the increased external pressure compresses the heliosphere, moving the heliopause closer to the sun. In emptier regions, the heliosphere expands. Scientists estimate the heliopause could move inward by 20 or 30 astronomical units if we entered a sufficiently dense cloud, bringing interstellar space significantly closer to Earth. What happens if the heliosphere shrinks too much? More cosmic rays reach Earth. More interstellar gas flows into the inner solar system. The increased radiation could affect satellites, spacecraft, and potentially even atmospheric chemistry. Some researchers suggest major changes in the heliosphere's size might influence Earth's climate over millions of years, though the evidence remains weak. What is certain is this: the shield protecting you is not fixed, it breathes, it flexes, and its strength depends entirely on what we fly through in the galaxy outside. Wrapped around our solar system like a tilted crown sits a sphere of frozen objects. The sphere extends from 2,000 astronomical units out to 200,000 astronomical units from the Sun. That is roughly 3 light-years in diameter, reaching nearly halfway to the nearest star. Inside this sphere, trillions upon trillions of icy chunks orbit in darkness, most smaller than a city, some as large as mountains. This is the Oort cloud, and we have never directly observed a single object inside it. The cloud's existence is inferred, not confirmed. We see comets entering the inner solar system from random directions, not from the ecliptic plane where planets orbit. These comets arrive from above, below, and all sides equally, suggesting they come from a spherical reservoir surrounding us. The math works. The orbital mechanics check out. The cloud almost certainly exists, but we cannot see it directly because the objects are too small, too dark, and too far away to reflect enough sunlight for our telescopes to detect. Astronomer Jan Oort proposed the cloud in 1950 after studying long-period comet orbits. He noticed these comets had orbital periods of thousands or millions of years and arrived from seemingly random directions. Something had to be nudging them out of distant orbits and sending them sunward. Oort calculated that a spherical cloud of icy debris at enormous distances could explain the observations. The idea stuck. The cloud was named after him. The cloud is divided into 2 regions. The inner Oort cloud, also called the Hills cloud, extends from about 2,000 to 20,000 astronomical units. This region might be donut-shaped, concentrated around the ecliptic plane. It is denser than the outer cloud, possibly containing tens or hundreds of times more objects. The outer Oort cloud extends from 20,000 to 200,000 astronomical units. This region is definitely spherical, surrounding the entire solar system, equally in all directions. Estimates for the total number of objects in the Oort cloud vary wildly. Conservative estimates suggest several trillion objects larger than half a mile across. More optimistic estimates reach tens of trillions. The total mass probably equals a few times the mass of Earth, maybe 5 to 10 Earth masses if you include everything down to tiny pebbles. These objects are pristine. They have not been heated by the sun significantly since the solar system's formation. They contain ice from the original molecular cloud that collapsed to form our solar system. Studying them would provide direct evidence of what the early solar system looked like, but we cannot reach them. The fastest spacecraft ever built, New Horizons, travels at about 36,000 miles per hour relative to Earth. At that speed, reaching the inner edge of the Oort cloud would take roughly 500 years. Reaching the outer edge would take 30,000 years. And something out there is shaking it. Something is disturbing those distant orbits, sending comets falling toward Earth. The answer lies in the galaxy itself. Between the outer planets and the spherical Oort cloud sits a structure scientists predicted in 1981, but still cannot directly observe. A donut-shaped swarm of icy objects packed far more densely than the outer cloud. This is the Hills cloud, and it might explain why comets keep falling toward Earth even after billions of years should have emptied the outer Oort cloud. The problem is simple. Objects in the outer Oort cloud orbit so far from the sun that their gravitational binding is weak. A passing star, even one coming within a few light years, exerts enough tidal force to strip comets away or send them into different orbits. Over 4.6 billion years, the outer cloud should have been depleted significantly, yet long-period comets keep arriving. The supply seems nearly constant. Jack Hill's proposed a solution. Maybe a denser reservoir sits closer to the Sun, inside the outer cloud sphere. This inner region would be more tightly bound by solar gravity, less vulnerable to disruption by passing stars or galactic tides. Objects in the Hills cloud could survive for billions of years, occasionally getting knocked into the outer cloud or directly into the inner solar system by gravitational perturbations. The Hills cloud probably extends from about 2,000 astronomical units to 20,000 astronomical units from the Sun. Its thickness might be several thousand astronomical units above and below the ecliptic plane. The density should be tens or even hundreds of times greater than the outer Oort cloud, meaning the majority of cometary nuclei in the entire Oort cloud complex actually reside in the Hills cloud rather than the better-known outer sphere. The Hills cloud matters because it acts as a reservoir constantly replenishing the outer Oort cloud. As objects in the outer cloud get stripped away by passing stars or scattered by galactic tides, the Hills cloud feeds new comets outward to replace them. Without this inner reservoir, the Oort cloud would have dispersed long ago, and long-period comets would have stopped arriving in the inner solar system billions of years before Earth developed life. The Milky Way is trying to tear apart the Oort cloud, not violently, not quickly, but continuously, relentlessly. The galaxy's gravity squeezes and stretches the outer solar system, distorting the orbits of comets at the edge of the Sun's influence. This force is called the galactic tide, and it is the main reason long-period comets fall toward Earth. Think about how the Moon creates ocean tides on Earth. The Moon pulls harder on the side of Earth closest to it than on the far side because gravity weakens with distance. This difference in gravitational pull stretches Earth slightly. The same principle operates on the Oort cloud, but the forces come from the Milky Way's mass distribution. The galactic tide is incredibly weak. At the distance of Earth from the Sun, the galactic tide is completely negligible, billions of times weaker than the Sun's direct gravitational pull. But at distances of 50,000 or 100,000 astronomical units where Oort cloud comets orbit, the Sun's gravity weakens dramatically. At those distances, the galactic tide becomes comparable in strength to the Sun's gravity. The two forces compete for dominance. The competition happens at a boundary called the tidal truncation radius. This is the distance from the Sun where the galactic tide becomes strong enough to permanently remove objects from orbit around the Sun. Beyond this radius, comets cannot remain bound to the Sun indefinitely. The tidal force will eventually strip them away, ejecting them into interstellar space. The tidal truncation radius sits somewhere between 100,000 and 200,000 astronomical units, defining the absolute outer edge of the Oort cloud. The galactic tide sends comets toward Earth by constantly tugging on them, slightly changing their orbits over millions of years. Sometimes the perturbations increase a comet's orbital energy, pushing it outward toward the tidal truncation radius where it might escape. Other times, the perturbations decrease its orbital energy, causing its orbit to become more elliptical. If the orbit becomes elliptical enough, the comet's closest approach to the Sun drops below a few dozen astronomical units. Suddenly, the comet enters the realm of the giant planets. Jupiter, Saturn, Uranus, and Neptune can now gravitationally interact with it, scattering the comet further. Most of the Milky Way is invisible. The stars you see, the gas clouds, the dust, all the normal matter that emits or absorbs light accounts for only about 15% of the galaxy's total mass. The rest is dark matter, and it surrounds the entire galaxy in a massive halo extending hundreds of thousands of light years into space. Dark matter does not emit light. It does not absorb light. It does not interact with electromagnetic radiation at all, as far as scientists can tell. The only way dark matter reveals itself is through gravity. Astronomers discovered it by measuring how fast stars orbit around galactic centers. The speeds were too high. If galaxies contained only the visible matter we can see, stars in the outer regions should orbit much more slowly, but the stars do not slow down. Galaxies rotate almost like solid disks, with outer stars moving nearly as fast as inner stars. The only explanation is that galaxies contain far more mass than we can see, and that mass must be distributed in a large halo surrounding the visible disk. The Milky Way's dark matter halo is enormous. Computer simulations suggest it extends at least 600,000 light-years from the galactic center, possibly farther. The total mass might be 10 times the mass of all visible stars, gas, and dust combined. This halo is not empty space. It is filled with dark matter particles, whatever those particles are. The dark matter halo contributes to the galactic tide acting on the Oort cloud. When scientists calculate the tidal forces squeezing and stretching the outer solar system, they must include two components. One component comes from the visible matter in the galactic disk, all the stars and gas we can directly observe. The other component comes from the dark matter halo. The dark matter contribution adds about 15% to the total galactic tide. That might not sound like much, but at the distances of the Oort cloud where forces are extremely weak, 15% matters. Above and below the galactic plane, out beyond the thin disk of stars where most visible matter concentrates, space fills with gas heated to temperatures that would vaporize any solid object instantly. This is the galactic halo gas, a diffuse plasma spread across hundreds of thousands of light years, glowing faintly in X-rays. The temperature reaches 1 million degrees Kelvin or more, hot enough to strip electrons from atoms and create a soup of charged particles. This hot halo is not the same as the dark matter halo. The dark matter halo is invisible and spreads even farther into space. The hot gas halo is normal matter, mostly hydrogen and helium with traces of heavier elements, but it is so hot and diffuse that it emits very little visible light. Only X-ray telescopes can detect it. Where does the heat come from? Two main sources. Supernovae. Explosions in the galactic disk inject enormous amounts of energy into surrounding gas. The shock waves from these explosions heat gas to millions of degrees and blast it upward out of the disk into the halo. This creates what astronomers call a galactic fountain. Hot gas rises, cools as it travels, eventually falls back down toward the disk under gravity, where it gets heated and blasted upward again. The cycle repeats continuously. The second source is gravitational energy. As the Milky Way formed, gas fell inward toward the center, converting gravitational potential energy into kinetic energy and heat. This accretion heating can raise gas temperatures to millions of degrees. Even now, the galaxy continues accreting gas from the intergalactic medium, and this fresh gas gets heated as it falls into the potential well of the galaxy's gravity. In December 2020, astronomers using the EROSITA X-ray telescope discovered something terrifying. Two enormous bubbles extend 14,000 light-years above and below the galactic center. That distance is half the radius of the visible Milky Way disk. These bubbles glow with X-ray light invisible to human eyes, marking regions where gas was shocked and heated to temperatures exceeding 2 million degrees. The bubbles are nearly symmetrical, one above the galactic plane and one below. Their edges are sharp, tracing collisionless shocks where hot gas slams into cooler surrounding material. What created these monsters? Two possibilities exist. Either a burst of star formation in the galactic center or activity from the supermassive black hole. Both processes can inject enough energy to inflate bubbles this large. Scientists estimate the total energy required equals about 100,000 supernovae exploding in a relatively short time, or 1 million solar masses of material falling into the central black hole and converting a fraction of that mass into radiation and kinetic energy. The timing appears to be millions of years ago, possibly 10 to 20 million years back. The bubbles are not expanding rapidly now. They appear to be in a late stage of evolution, coasting outward slowly as they age. The discovery reveals information about the galactic center's history. The Milky Way's central black hole is quiet now. It accretes material slowly, producing relatively little radiation compared to active galactic nuclei in other galaxies. But the bubbles prove our black hole was not always dormant. At some point in the past 10 million years, something fed the beast. A gas cloud fell in, or stars ventured too close and got torn apart, or perhaps a smaller galaxy merged with the Milky Way's core. Whatever happened unleashed enough energy to blast gas 10,000 light-years outward from the plane. Every second, hundreds of high-energy particles slam into Earth's atmosphere from above and below. These cosmic rays, despite their name, are not rays at all. They are atomic nuclei, mostly protons, accelerated to nearly the speed of light by violent processes across the galaxy. They rain down on Earth continuously, invisible and unstoppable. Most cosmic rays come from supernova remnants. When a star explodes, the blast wave expanding outward accelerates particles to relativistic speeds. The shock front acts like a cosmic particle accelerator, bouncing particles back and forth across the shock until they gain enormous energies. But some cosmic rays have higher energies, much higher. The most energetic cosmic ray ever detected hit Earth's atmosphere, with energy equivalent to a baseball traveling 60 miles per hour, all concentrated in a single atomic nucleus. Nobody knows how natural processes can accelerate particles to such ridiculous energies. Cosmic rays do not travel in straight lines from their sources to Earth. The galaxy's magnetic fields deflect charged particles, causing them to wander through space in random zigzag paths. A cosmic ray might travel thousands of light years through the galaxy, bouncing around magnetic field structures before eventually reaching the solar system. Ray flux increases. There is a line in space beyond which nothing can remain bound to the sun. Not planets, not comets, not spacecraft. At this boundary, the Milky Way's gravity becomes stronger than the sun's. Objects beyond this line belong to the galaxy, not to our solar system. This is called the tidal truncation radius, and it marks the absolute edge of our solar system's gravitational dominance. That edge sits somewhere between 100,000 and 200,000 astronomical units from the sun. The boundary exists because gravity weakens with distance. Close to the sun, solar gravity dominates overwhelmingly. The sun pulls on nearby objects far more strongly than the galaxy does, but move outward and the sun's pull weakens rapidly. Meanwhile, the galaxy's tidal forces stay roughly constant because the scale of the galaxy is so much larger than the solar system. At some distance, the two forces become equal. Beyond that distance, the galaxy wins. What happens at the tidal truncation radius? Objects orbiting the sun at that distance feel equal gravitational tugs from the sun and from the galactic tide. Their orbits become unstable. Small perturbations, which closer in would cause only minor orbital changes, now can eject objects entirely. Over millions of years, the galaxy strips away any objects orbiting near or beyond the truncation radius. This is why the Oort cloud has an outer edge. Comets cannot survive beyond the tidal truncation radius for billions of years. The galaxy removes them. The outer boundary of the Oort cloud at roughly 200,000 astronomical units coincides with where the tidal truncation radius is calculated to be. It is not a coincidence. The galaxy itself defines where our solar system ends. The exact location of the boundary depends on which direction you look. Toward the galactic center, tidal forces are slightly stronger, bringing the truncation radius closer. Away from the galactic center, tidal forces weaken slightly, allowing the boundary to extend farther. The Oort cloud is not a perfect sphere. It is slightly elongated, stretched along the line pointing away from the galactic center, where solar gravity can hold objects at greater distances. Calculating the tidal truncation radius requires knowing the galaxy's mass distribution, including both visible and dark matter. Uncertainty in the dark matter halo's properties translates directly into uncertainty in where the boundary sits. Different models place it anywhere from 100,000 to 200,000 astronomical units, a factor of 2 range that reflects our incomplete knowledge of galactic structure. Beyond the tidal truncation radius lies interstellar space, not just in the sense of being outside the heliosphere, but in the deeper sense of being outside the sun's gravitational domain. Objects that do not orbit the sun. They orbit the galactic center, influenced primarily by galactic gravity. If the sun has objects beyond the truncation radius, they are not part of the solar system anymore. They are independent interstellar objects that happen to be passing near the sun temporarily. The concept applies to all stars. Every star has its own tidal truncation radius beyond which the galaxy dominates. Stars in dense regions near the galactic center have smaller radii, because nearby stars contribute additional tidal forces. Stars in the halo far from the galactic center have larger radii, because local tidal forces are weaker there. The sun's truncation radius is typical for a star at our galactic location. Some scientists speculated that the sun might have had a much more extensive Oort cloud initially, perhaps extending several times farther than it does now. Encounters with passing stars and gradual erosion by galactic tides stripped away the outermost comets over billions of years. What remains is the inner core of the original cloud, the region close enough to the sun that even after 4.5 billion years, solar gravity still holds it. The tidal truncation radius represents the ultimate boundary. Beyond it, you are no longer part of the sun's realm. You belong to the galaxy. Everything above and below the solar system, all the structures described here, exists beyond this boundary or spans scales far larger than it. The local bubble extends 1,000 light years. The galactic halo reaches hundreds of thousands of light years. Dark matter surrounds the entire galaxy. We are a tiny system embedded in structures vastly larger than ourselves. The sun's gravitational influence extends just 3 light years at most. Beyond that, the galaxy takes over completely. What lies above and below our solar system is not just empty space. It is a galaxy-scale environment filled with hot gas, magnetic fields, dark matter, cosmic rays, stellar streams, and ancient structures shaped by billions of years of evolution. We float in that environment, protected by distance and by the sun's local dominance. But the boundary is there. The galaxy surrounds us, and at the edge, the sun's power finally ends. The galaxy waits beyond.